We now know how our world ends. Our affinity with sci-fi movies and perhaps the Bible would point toward the big bad apocalypse. But what if we told you that the end of the universe is no different than its inception? The James Webb Telescope has revealed that the universe has stopped expanding. Popular scientist Brian Cox made this prediction years ago. In doing so, he gave us the most realistic starting point to imagine the end of the world. We can look to light that began its journey before there were galaxies, the oldest light in the universe as evidence. So if people don't believe in the Big Bang, the answer is, well, you can see it. We're heading towards Big Bang 2.0. Join us as we explore why the world has stopped expanding and James Webb's terrifying discovery. If we're certain about anything in our knowledge of the universe and its history, it's the fact that our very epoch of existence is centralized around this event called the Big Bang. Of course, there are alternative theories that recognize the beginning of the universe, such as eternal inflation or an oscillating universe, but we're not getting into the validity of these theories today, mainly because the astronomical community has now readily accepted that our history in this universe starts with a Big Bang, and the ideas that succeed the Big Bang are also based on the same common point of the universe's birth. While the Big Bang is a common term in the theoretical knowledge of astronomy and space, we're hardly aware of the hows and whys of the phenomenon unless you're a nerd who has spent hours watching some excellent visualization of the Big Bang. To be fair, the phenomenon was more than an explosion, or so to speak. Simply put, the Big Bang finds its origin in a single point, a point that was infinitely hot and dense that inflated to extreme lengths. All of this was when the universe was incredibly young. Believe it or not, at the time of the Big Bang, the universe was only 10 to the power of 34 seconds old. That is 1/100th of a billionth of a trillionth of a second in age. And this is when the universe experienced an incredible burst of expansion, aka the infamous explosion or inflation. During this process, space expanded faster than the speed of light, so yeah, you wouldn't have even blinked when the universe grew 90 times in size almost instantaneously from subatomic size to golf ball sized. 1 second after the inflation, the universe began to cool, which led to the formation of matter as we know it today. So yeah, as far as the timeline goes, within a second, our universe was full of every particle we've learned about in our chemistry class, willingly or otherwise. Protons, neutrons, electrons, anti-electrons, photons, and neutrinos are the legacy of the Big Bang. Magical, right? Well, figuratively it looks like it, but our understanding of the universe's inception is highly theoretical. We've come a long way since the first moon landing, and since then, our technological advancement has grown exponentially. Back when scientists were studying the Big Bang, they were only based on mathematical formulas and scientific models. They wouldn't have imagined that we'd be exploring the possibility of life on Mars. There have been some big breakthroughs in our pursuits to study the universe and explore space, yet even then, our existing technology is pretty limited. You see, we can't recreate the Big Bang or peer back at the event itself. Our biggest piece of evidence comes from the cosmic microwave background that has allowed scientists to observe the echo of the Big Bang. While this mechanism is groundbreaking in the study of the universe, it's also theoretically limited. The biggest barrier in this particular methodology is the fact that we can't see the gravitational waves or the residual radiation that came from the expansion itself. So while our entire knowledge rests on theoretical tenets, scientific theories have a large room to be disproved as well. Yep, we're pretty sure about the Big Bang as the concept and how it was monumental in creating our universe, but there are some chunks of its aftermath that we've gotten wrong, and as shocking as it is, theories about our universe are largely based on data that is prone to human errors all the time. At the same time, some of our data is also highly conclusive about the Big Bang. Let's just say that at this point in time, it's not easy to disprove the theory altogether. Is our universe still expanding? In the last decade or so, our only saving grace to study the Big Bang was the Hubble Space Telescope, and now, of course, all bets are on the excellent precision of the James Webb Space Telescope. Before we got to use these powerful technological instruments, one of the biggest points of contention in astronomical study was the expansion of the universe. If you pick up some science textbooks from the early 90s or so, you'd read about how the universe is widening, in other words, the universe is expanding. But the real snafu here is that perhaps we don't understand what the expansion of the universe entails, and more importantly, we've got to ask ourselves if the universe is actually expanding because, spoiler alert, the James Webb Space Telescope is telling us otherwise. Lo and behold, the universe has stopped expanding. And now, before jumping into the implications of this groundbreaking shift from our universe's trajectory, let's just talk about our understanding of this perplexing phenomenon in the first place. The most common knowledge associated with the Big Bang characterizes it as an explosion, and well, fiction and popular media have put solid imagery to this process as, well, any piece of media would depict the inception of the universe as some sort of a blast that hurls tons of energy and matter just spread in every direction. Scientifically speaking, that sort of visualization isn't correct. Despite the widespread use of the explosion and inflation of the word, the birth of the universe wasn't exactly a blast. Scientists want us to correct our understanding of the universe. In NASA's own words, the universe did not expand into space, as space did not exist before the universe. Instead, it is better to think of the Big Bang as the simultaneous appearance of space everywhere in the universe. Our understanding of the phenomenon also reveals that our universe has lived through a durable cosmic period that was only disrupted by the reunification in space. Before that particular chemical conjecture, our universe was just pitch-black dark. The "let there be light" moment of the universe only occurred 400 million years after the Big Bang. Yeah, that's right. You see, the big explosion only created the basic tenet of all living beings and heavenly bodies in the universe. For 400 million years, the universe was plunged into darkness because, well, it's simple, there were no stars or galaxies. When that was rectified, as clumps of gas turned into stars and galaxies, only then did the universe get out of its cosmic dark ages. So here's a little trivia for you guys. When do you think our solar system came into being? If the universe was just darkness and eeriness for 400 million years, well, our solar system was born 9 billion years after the Big Bang. So yeah, sorry sci-fi movies, there's a huge disconnect between the so-called explosion and scientific theory. And of course, this changes everything. The way things are, our universe still exists as a single inception point. It hasn't moved or expanded ever since the Big Bang. What really happens is that space has been stretching over time, and it carries matter with its trajectory. To put it in clear-cut words, the universe isn't expanding the way we visualize it or even understand it. It is actually the active stretching of space that precedes the expansion of the universe. We know it's a bit complicated to comprehend this, but it's also important to understand the implications of what we're about to tell you. For the purpose of this video, we continue to use the phrase expansion of the universe to signify the active movement of our space, mainly because even scientists are comfortable using the exact framing to describe the recent discovery made by the Webb Space Telescope. The fact that the universe has stopped expanding is both terrifying and inconsistent with our previous theoretical knowledge of this baffling phenomenon. Because you see, before this shocking discovery, scientists were convinced that the universe was expanding at an accelerated rate from its inception. And well, they weren't wrong. With the help of the Hubble Space Telescope, scientists were able to gather concrete evidence to support their theory. So no, this isn't the case of NASA correcting its earlier understanding of the universe's expansion. Whatever is happening to our universe, it's entirely new and possibly irreversible. While the discovery itself is profoundly frightening, it isn't overly unexpected either. As we talk more about gravity, you'd see that our universe was always susceptible to a recollapse. In the case when the universe had an ample amount of energy density, its expansion would stop entirely. By the looks of it, our universe is going backward. Back in the 1990s, NASA and its credible scientists had some very conclusive ideas about the expansion of the universe. The most fundamental unit of their scientific understanding was gravity. While that much still remains true today, we have some entirely different ideas about the speeds at which our universe expands. As we've already discussed earlier, scientists have a theoretical prediction about the universe's recollapse that would cease the expansion as we know it today. But also, the contesting idea was equally terrifying, if not jarring enough. Too little energy density would mean that our universe would never stop expanding. The uncharted bizarreness of the idea is quite limited today, but you see, it was the 1990s, and scientists had little technological help to find tangible or observational data for their predictions. What they were certain about was that as our universe ages, gravity would definitely decrease the rate of expansion all over the course of time, of course. And even intuitively, it makes sense. Gravitational pull brings galaxies together. This is something we've already established. So as the universe would expand, the gravitational force would resist widening the distance between the heavenly objects. Since our universe is just a patch of matter, the attractive gravitational pull would keep the matter intact. This theory was also extended to understand the rate of the universe's expansion. Scientists believed that since gravity is the binding glue for all of the matter and has existed since the universe's inception, the rate of expansion had to slow down. Sure, we didn't have any means to observe this phenomenon or carry out some big data testing, but theoretically this made complete sense until it didn't. In 1998, the invention of the Hubble Space Telescope changed everything we knew about the universe. The Hubble Space Telescope was effectively used to study the distant supernovae in our universe that explained the fluidity of our space. This is to say, scientists employed supernovae to study the expansion of the universe. What they found out was completely opposite to what they knew about our universe, and let's just say scientists were left completely dumbfounded and clueless. After all, the whiplash was monumental. Not to mention the single discovery meant that astronomical studies had to be inherently rewritten and revised. Scientists had to look back at their theoretical studies and change everything on the basis of what the Hubble Space Telescope showed them, and there was no room for error in judgment. For the first time in the study of the universe, seeing was believing. It had turned out that gravity wasn't slowing the expansion of the universe at all. In fact, the universe was expanding at a higher acceleration than it had ever before. You heard that right. Ever since the universe's inception, the rate of expansion had only increased from its earlier data points. For the most part, this unexpected theory was hard to explain. Of course, gravity couldn't cause the faster acceleration. If anything, gravity should have fought valiantly to decelerate the rate of the universe's expansion. But by all accounts, gravity was rendered powerless. In fact, to this day, we don't know how or why the universe was expanding to astronomical degrees. As per theoretical knowledge, the expansion should have slowed down until there was an anti-gravitational force in the universe that was effectively overpowering gravity. And until the recent discovery of the James Webb Space Telescope, scientists were mostly of the opinion that our universe is a huge battlefield. Here's why. You see, after Hubble's discovery, the scientific world was in a crisis. Agencies like NASA wanted quick explanations for the unprecedented cosmic acceleration. Our first guess was that perhaps Einstein's theory of gravity isn't as accurate as we thought. As per the theory, we had started to recognize gravity as a distortion of time and space that is caused by mass and energy. In theory, gravity wasn't just a force. It could wrap around mass to push it or pull it. So if this theory stood correct, the universe shouldn't have been expanding at accelerated rates. Another thing that could explain the phenomenon was some energy fluid that hastened the expansion. Now, there were a lot of contesting theories that came and went away. Nothing really stood its ground. Eventually, the possibility of falsifying Einstein also went away. Today, the only answer to Hubble's astounding discovery can be summarized in 2 words: dark energy. Yep, now you know why this throwaway word in science is so important. But you'd be surprised to know that we don't know anything about this force. None at all. The only thing we know is that it makes up the majority of our universe. It's almost frightening, but the normal matter just constitutes 5% of our universe. The rest is just dark matter and dark energy. This also proves Einstein's notorious cosmological constant, the way Albert Einstein explained empty space. It was always an entity with its own force, and as the universe expands, this force wouldn't change or get diluted even to the slightest. So how's this related to what the James Webb Telescope shows us? Why has our universe stopped expanding in the presence of dark energy? Well, scientists are still getting comfortable with the bizarre discovery, but if we had to look at the optics of the duel between gravity and dark energy, we might have an answer. The cosmological constant is the enigmatic force in space that can be substituted for dark energy. The scientific theory suggests that gravity and dark energy are always in a battle with each other. It's just about what gets the upper hand, what overpowers the other. Before our universe stopped expanding, it seemed like dark energy was giving gravitational pull a run for its money. In doing so, our universe was expanding at accelerated rates. Now this phenomenon has halted completely. Considering that our knowledge of space properties and dark matter was already profoundly limited, scientists have no trajectory to explain this disruption whatsoever. While NASA was already expecting anti-dark energy to emerge, this particular notion of physics wasn't anticipated in the current epoch we live in. By all means, the halt in the universe's expansion, as Brian Cox would put it, is entirely new physics. Of course, one simple and logical explanation could be that gravity is finally overpowering dark energy to stop the expansion of the universe. Because if our universe has a trajectory, it would have at least contracted to a considerable degree before the expansion stopped altogether. Or maybe gravity started to cancel the effects of dark energy out of nowhere.